So, then welcome to the lecture number. I just recognized that I lost the number, whether this is 12, 13 or whatever. In Introduction to the Lattice Boltzmann methods. Since this is the second to last lecture, so we'll have one lecture more next week, and then that will be the last one. So we are now a little bit in the advanced topic section already, yeah. And we cannot cover everything, but there are a few things that are potentially not in the books, which we want to cover today, yeah, because this is also things that you don't find really in the papers. There's always a part of a subject where you have to ask the people who are actually doing it how it is actually done stuff, yeah. Okay, and the thing here is the efficient implementation of the cumulant method. Interesting historical fact is that the idea to use the cumulants in the Lattice Boltzmann method has been around for a pretty long time before actually there was a working cumulant method, yeah, because it turns out that this is technically difficult to implement cumulants. And so we had to overcome some technical difficulties to actually be able to implement a cumulant method that actually does what it's supposed to do, namely being a much more accurate and stable solver that can run at that can produce much better results at lower resolutions than, for example, MRT or BGK methods. Okay, so unfortunately we have a little bit of text, yeah, which we go over. I'm not. You can download this later. Maybe you'll keep some space in your paper and write it afterwards, yeah. So I want to go through these few points. Yeah. One aspect of the cumulant method is because cumulants are not easily computed, they have a lot more floating point operations per node update as would be the case in BGK and MRT, which has some ramifications on the performance, yeah. By performance, I do not necessarily only mean the time of execution, yeah. So obviously you could say so more operations, so potentially it takes more time, which you may be willing to pay if it is then more accurate, yeah. Of course, the question is how many more operations. So we've seen. In the example that we programmed it only in 2D, and I told you, yeah, so you have an exponential growth in effort with the dimensions. So in 3 dimensions, computing cumulants is pretty complicated and especially pretty expensive. Yeah, the equation is getting very, very long, and you have many cumulants that you have to compute. However, compared to when I was young, maybe this is not news to you today, but I remember when this was news, yeah. What is expensive today on computer is handling memory, yeah, reading data from memory and writing data to memory. This is the expensive part. Yeah, because this has to go through the bottleneck of a bus. And this is usually much more expensive than just doing floating point operations. Yeah, so computers become better and better and better in doing floating point operations. So in general, you could think, and this is even sometimes the case, that a cumulant method and a BGK method do not distinguish themselves a lot in their execution speed, yeah? Because both of them use the same data, yeah? So they read and write the same data. They only differ in the number of floating point operations that they do, but the floating point operations themselves are not that expensive. And what you could do in principle, and this is the reason why it may actually be no difference in this, is that modern computers can concurrently read and write from memory and do the floating point operations. So if you implement your code in a very careful way, it could be that the floating point operations do not cost anything with regard to time, yeah? Because they are all done during reading other data, yeah? So that is a possibility, yeah? So, and usually for BGK this is even the case. So just doing BGK or just reading and writing it back usually has the same cost, yeah? So this is, okay, but this may require specific implementation, in particular when we are talking about not only the communication between the processor and the main memory, but if you have a parallel implementation where you also have to communicate with other compute nodes. Yeah, so over a network. Yeah, so then we have to also this communication can be overlapped, and then we call this communication hiding. But also on the processor, when we use caches, this is called communication hiding. So LBM, as a general rule, is not always true, but in general, usually, is bandwidth limited. So the ones who come to my parallel programming lecture, yeah, they know what bandwidth limited is. This is what I just said. The execution speed is dictated by how quickly memory can be accessed and not by how many floating point operations can be done. However, with the cumulant methods, we have so many floating point operations that that this method will become dominated, can easily become dominated by these floating point operations, in particular if you have a naive implementation thereof. Yeah, so if you have I remember the first cumulant implementations, they were 10 or even 50 times slower than a BGK. Yeah, so in orders of magnitude slower. Yeah. There's no longer the case, yeah? So, and then there is something that I find very important and which is often overlooked by, people who get started with this, is that we do not own, that time is not everything, yeah? Time is not everything, yeah? If you have more operations, this also means you have more errors. Yeah, you have more round of errors. And this is something that people who work with iterative methods may not recognize, or that is not relevant to them. So in numerics, in general, there are many implicit iterative algorithms, yeah, that solve equations iteratively. So if you think about it, these iterations are an optimization problem where there is an error that they, a reminder that they optimize away, yeah. So if you make a round of error in one iteration step, this will just add up to your error that in the next iteration step you will try to eliminate, right? So, for that reason, these iterative methods, as a general rule, are relatively immune to round-off errors. Whereas if you have explicit methods, for which the Lattice Boltzmann is an example, you know, you have never a correction step. Whatever error you do, yeah, you will keep forever. Yeah? And for this reason, and this is also true for other explicit methods, the accumulation of round-off errors due to having many operations is a very serious problem to the Lattice Boltzmann method. And this actually is a more serious problem than the execution time. Because execution time, okay, you could talk execution time away. So saying we have, even saying the cumulant method is an order of magnitude slower than the BGK method, yeah, but we get better results and we are scientists, we just want to see whether it works. Forget it. The problem why cumulants in the beginning didn't work was that if you implement them in a naive way, and in a sense this was what we did, so remember we first did a transformation to the raw moments, then we transformed the raw moments to central moments, then we transform the central moments to cumulants, then we do the relaxation, then we go back to central moments, then we go back to raw moments, then we go back to F. Yeah? So we have 6 transformations in one collision step. Yeah? One after the other. In each time you lose data by round off. Yeah? So, and imagine this in 3 dimensions. Yeah? With equations that go over 27 pages. What we observed was we did not get the result that we want to see. No increase in accuracy due to this many round-off errors. Yeah? So actually the round-off errors is the bigger problem than the execution time. Okay, and because this is the bigger problem, this is also what we are going to talk today the most. So, okay, I spent now more than 10 minutes of this on just talking about the text here. Maybe you've had enough time to write it anyway. So, let's go actually to the lecture. First, let us understand how round-off errors work, in particular in the world of Lattice Boltzmann. So there are 2 things that we have to distinguish, namely the data loss in storage and the data loss in calculation. Yeah? So we start with the data loss in storage. Data loss in storage. So what is storage? What do we want to store? Let's begin with this. So we have our populations. So let's say we are in 3 dimensions where we usually are and where the problem is much bigger than in 2 dimensions. So we have this Fijk. They are actually superpositions of the moments. Of moments, say the raw moments MABC. So you can always, and this is, because this is raw moments, this does not depend on anything else. You could say that's Fijk, yeah. So you remember the old days where there has just been this matrix. So you can think about the matrix like this. There is a value alpha I J K that and ABC that communicates between the moments MABC and the distribution. So what I want to say is there is a weighted sum. So for every population, yeah, there is a weighted sum over all the moments that gives you this population. So this is the inverse transform from coming from populations to the moments. Yeah. So this is what I mean. The populations are superpositions. There are some summed up part of the moments. So, and the thing is that the thing that has to be stored is the population. We have to store the population because the population is the thing that streams. This is the thing that we shift in memory, right? So we have to store them. Otherwise, there is no streaming. So then the populations, they are stored in floating point numbers. So, and floating point numbers, of course, you know that there are different kinds of floating. There is a standard which is often not really well implemented. This is the IEEE 7554. And we look at it for 32 bits. So actually, what I find interesting, so in the old days, when I was your age, 25 or so years ago, yeah, then everybody went to larger and larger and larger floating point numbers. Yeah. Nowadays, with artificial intelligence, it has become fashionable to go to smaller and smaller and smaller floating point numbers. There are even 8-bit floating point numbers, I learned, or something like very, very tiny floating points, so half precision, quarter precision, yeah, thing. So we run our example code with double precision sometimes and with single precision. Yeah, so this is what is usually used. We'll talk about single precision here because single precision actually is used a lot in industry applications because it is much faster than using double precision. Yeah. So usually at least twice as fast. So if you can deal with single precision, it's much better. So but I mean, everything here applies also to double precision, just at a different level. So let us look at the definition of 1, 2, 3. Okay, I'm not trying it to scale. I'm not trying it to scale. It's just maybe a little longer. Okay, you may want to draw it by to scale, but this is not. You see, this is, we said 1 bit here. We say 8 bits. So, and we said 23 bits. Should write this in the same way. So this is how we split up our floating point number, and the first bit, this first bit here is the sign. Could potentially, these 8 bits are the exponent, and these 23 bits are the fraction. So this is where the actual number is. Yeah. So the exponent tells you where you put your floating point, the position of the floating point, and the fraction tells you what is your actual number. So this is if we calculate in single precision, this is where we have to store our populations.
This one is single precision.
This one is single precision, 32 bits. Yeah. So, and if you have, I mean, sign is always 1 bit, but in a double precision, the things, well, get larger. I'm not exactly sure that how they become larger. I think that this here will become 16 bits, and this here will potentially be 46, but I'm not completely sure. Yeah, that doesn't matter. I mean, we are talking about the principle here. Yeah. So So all moments, this is an important thing, share the same space. Because there's a superposition of them, they share the same space in the fraction. So, and this is a problem because, as we learned from asymptotic analysis, these things come at different sizes or scales. Okay, you all know that I like diffusive scaling. Let's do this in diffusive scaling. So diffusive scaling, this is something that you need to know in the exam. Delta t is delta x square, is proportional to delta x square, and this is what we call epsilon, so the smallness parameter. Okay, I mean, this is so essential, you don't pass the exam if you don't know this, right? So this is our smallness parameter, epsilon, and the epsilon square is proportional to delta t. So then, according to our asymptotic analysis, we have parts of our moments are of order epsilon to the power of 0, so they are constant. This is the density, is the 0 order part of the density. We have at epsilon to the power of 1, we have velocity. We have epsilon times u, first order of velocity. And then at epsilon square, we have things like pressure, but we also have things like the stress, which I'm not writing now. So this is delta rho. So this is the second order of rho. Yeah. So the 0 order is constant, and the second order is proportional to the differential pressure, because there's a background pressure, yeah, that's always there, but we are only interested in the variation of the pressure, right? Navier-Stokes equation only depends on the variation of the pressure. So we have pressure and variation of the pressure. The pressure is of order 0, the variation of the pressure is of order 2. So, and yeah, okay, so as a reminder how this works, so we do not store these things. We do not store U1. Yeah, this is nothing that we have. What we have is we have U. Yeah, and U is composed of epsilon u to the first order, and this is the solution. And then there come other parts, epsilon then to the third order for velocity, with the third order of velocity, and further parts of higher epsilon, and they are called, these things here are called the error. Yeah, so they also exist, but they are the error. So what we are not able to store the solution. We are only able to store the solution plus the error. Yeah? This is the only thing that we have. So, problem in the storage is we have to say that epsilon to the order of 0, this is the smallness parameter, which by definition means that epsilon to the order of 0 is much larger than epsilon to the order of 1, which is much larger than epsilon to the order of 2, and so on and so forth. Yeah, so these different things, they have different sides, or we say different scales. So the variables that we have to deal with are, we will say, scale separated. The one is much larger than the other. So, scale separated, one much larger than the other, can be an advantage. Here it is not, because they are in the same space. The same space in the fraction. So, and now we look at this. We draw a picture to try to understand what that actually means. So say this is my fraction. And my fraction has, so there's big endian and little endian, yeah? If you've heard about this, but don't worry, we say here, we put on the left, we put the most significant bit. So this is where the largest thing is, yeah? And back here we have the least significant bit. Okay, I assume that you have enough understanding of a computer that you've heard about most significant and least significant bit in a number.
No, but what I'm thinking is that the one that has more weight is going to be at the beginning.
Yeah. Okay. Say we are now in we are in a small integer range, yeah, and we have only, what is it, 7 bits. Yeah, so then you would have a range from 0 to 126, 7. I don't 7 or 8, 7 because it's 0 included. Yeah. So, and okay, 7-bit is a little bit strange, but say this is what you would have. So then the most significant bit is the one, or in a binary number, yeah, the most significant bit is the one on most left, and the least significant is the one most right. Yeah.
It's because they go 0, 1, or 1.
Yeah. So so they are ordered as you would write them in on paper. Yeah. So at least we order them like this. That there are computers that do this differently. This is why there's a distinction between little endian and big endian. So, but so back then in the days when you had a lot of power processors, for example in the Mac, yeah, so there was a time when there were Macs around with power processors and Macs around with Intel processors. And the power processor had the numbers, the other way than the Intel processors. So they were pretty incompatible, therefore. Yeah. Okay. They could not use the same data. So, but this is history. This is nothing that we want to talk about. The thing we want to talk about is that in this fraction here, we put all our moments in a superposition, which means that we have things of very different size in here, and the largest thing will be located at the most significant bit, obviously. Yeah, and the largest thing is the constant part, rho 0. So then the other things will be smaller. For example, the velocity u to first order will be located here, and likewise the density, what is it? The pressure, so this is the second order, the pressure, but also the stress part, so dx ux to first order. This will start from here, and then you will have ghost moments where you potentially don't care that much, starting from third order, but you'll also some that are of lesser order. So what does it mean? It means that for this constant density part, we can place this very accurately, yeah, because we have all the space available for the rho zero, yeah. For storing the velocity, we have less space, and for storing the pressure, we have even less space, and for the ghosts, we have even less space yet. So no, I made a mistake again. So what this means, this here are the effective bits, the effective, okay, let's say the effective number of bits available for each quantity. So all of them share the same fraction, which means the number is stored with a given exponent, right? So this means that the pressure is stored at a lower precision than the velocity, and the velocity is stored with a lower precision than the background density. Okay, let's look at an example what this means. Okay, say rho zero as, okay, so the background density is 1. I mean, this is a reasonable assumption, yeah, so, and say now the velocity must be smaller than 0.1. This is more or less the absolute limit that we can handle. So let's be generous and say it's 0.01. And usually it's much, much smaller in practice, yeah? Delta x by delta t. So if this here is now first order, yeah, then our pressure is second order. So if it's second order, it means it is proportional to the u square. Yeah, it is proportional to the u square, so it does not need to be exactly u square. Yeah, but it is of the order of u square. So it will be of the order of 0.0001. Okay? Then the reason why they are all in the same place is because the zero part is the largest, and the largest defines the exponent. The exponent of the float. Okay, when I write float, I mean the floating point number.
Here I have a question.
Yeah.
Meaning that the exponent is going to see that we are, for example, if the density were 1e to the 3, for example, the exponent will
The exponent will shift.
To 1e to the 3, and then all of them would be written in terms of e, 1e to the 3.
Yes.
Okay.
Yeah. So the largest number that you have to store in this. This will simply define where you put your exponent, because the floating point number is that they will always put it like this, that there is a binary 1 in front of the number, and the rest is the field. So, which means that this rho 0 is stored in all 23 bits. So now I'm actually going through the pain of writing this down, and so there's a little bit of caveat, but so don't take us to be too accurate with this 23 bits now, because the thing is, as it is implemented, and I'm not absolutely sure about this, so I may make a mistake here. But the thing is, you actually have 24 of them, because you always know you are not storing the one in front of so you have the way they are stored is as point, just a point, and all the numbers behind it, because you always know that there is a 1 in front, so the 1 in front is not stored, so you actually have 24 bits. The only thing is you need to have some trick to actually store a 0, where you somehow use the exponent together with this, because otherwise, because if you always assume that there's a 1 in front, you cannot store a 0. Yeah. So there are few numbers. There is a few ways to represent other things than numbers, than these numbers. For example, infinity, minus infinity, and not a number, and so they are all also somehow stored with some way if the exponent is in a certain strange way. Yeah. So, but this is detail. It's not so important. Let's say it's 1, and then we have. Okay, so these are 6, then these are 9, then these are 12, then this is 15, 15 and 18 and 21, and then there are 2 and binary. Okay, so this is how we would store this 1. Yeah? So actually this is all 0. So let's see how we store this u. Actually, u divided by row 0, yeah, I mean, it's divided by 1, it's the same. Can forget this. Okay, so there is no unit here, because we just store the number. And now I'm just hoping that I have this correctly on my paper, so we get in binary number 0, 0, 0, 0. So now we have a 0 in front, yeah, because this is overloaded. It's put on top of the other number, yeah? 0, 0. So we get 7 bits of this is lost. Then we get 1, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 1, 1, 0, 0, 0, 0 in binary. So I did not check it. Maybe maybe I make a mistake, but this is what I've written on my paper. Yeah, and then we look at the pressure. The pressure which we set is 0.0001 would be 0.000000000, and then 1101001000 binary. And here what we've lost is 14 bits lost. So see, in that case, there's only 9 bits, should now be 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, okay, it's 14, yeah, okay, so 10 bits left, yeah, 10 bits out of this 24, 23 are left, so less than half of them are left for storing the pressure. Okay, so let's write this down. What is time? Okay, we are using to taking over time. In this case, 7 bits of the fraction are lost at each order of epsilon. Yeah, so you can imagine you add 7 more, then you are left with 3 bits, only 3 bits for the next ghost moment. Yeah? So, but this is of course just this particular case. So there could be other cases when the velocity would be smaller. So the number of bits lost depends on the magnitude of the epsilon to the order 1 variables. So this means usually the velocity. So now we are in trouble because we have competing interests, if you will. So why is the velocity a certain way? Yeah, the velocity is a certain way, not because it's physically that way. We have dealt it in delta x by delta t. Yeah, so we control the grid spacing and the time step, and we want the grid spacing and the time step both be small, and the time step even smaller, in order to get an accurate solution. Because this is what asymptotics tells us, yeah? Make the smallness parameter go to 0, yeah? So then you get a more accurate result, because you get rid of the error terms that come out of the Taylor expansion, for example. Now here we have completely the opposite problem, yeah? If we make the time step smaller, the error goes up. This is what this says, yeah? Because you make the velocity smaller, the error goes up. So the smaller the time step, the smaller in numerical units u is in units. I mean, we are talking about asymptotic scaling, of course. The even smaller are moments of higher asymptotic order. Okay, now we can look, for example, at just what is the maximal ratio of the smallest to largest variable. Okay, under the assumption that the smallest variable is represented by a single bit, which of course makes no sense at all, but let's think about it like this, yeah? Leaving only a single significant bit for the smallest variable. So this ratio is 2 by the power of 23 is 838. No, wait, it's not, is, okay, I'm too stupid to read it, so I write it. So this is this number. So this is thousands. So it's 8 million. Yeah. So it's 8,380,000 round. Yeah. I mean, now in an example that we are looking at velocities that are smaller, 10 by the power of minus 4, then epsilon square rho, so they are then 10 by the power of minus 8. So this here is 10 by the power of almost 7, right? Almost 7. So this is much smaller than this 2 by the power of 32, which means, think about this. If you have a flow with a velocity, with velocities that are smaller than 10 by the power of minus 4, delta x by delta t, if this is your case, then this solution will have no detectable pressure. Or let's say they will not have any detectable variation. Okay, let's write variation. In pressure. So, and this is not a joke or something, but this is something that you observe in practice. You implement your, you just write this, you take the theory, you write down your code, yeah, without thinking about round-off errors, and then you think you should do a convergence study with your code, yeah. So in order for your convergence study to work, you do diffusive scaling, you make the time step smaller and smaller and smaller. So actually you do the velocity smaller and smaller and smaller numerically, yeah, at same Reynolds number. And then you want, for example, measure whether your error in pressure, and you see, if you use single precision and you arrive at a velocity of 10 by the power of minus 4, you will not detect pressure. There is no more pressure in your solution because just the pressure does not fit in your memory. Yeah? This is something that you can observe directly. Okay, so what to do about this? Of course, this is a solved problem, but we have to be aware. So the solution to this is, the solution methods for this are called conditioning. And with conditioning, we mean the reformulation of a problem such that it is less prone to problems with round-off errors. So conditioning is the reformulation of a problem with the aim to reduce numerical erosion. Okay, round-off errors, this is kind of, way to describe this, on numerical erosion due to rounding. I mean, the disappearance of information because you are using floating point numbers. So if something is not conditioned or not well conditioned, then we call it poor conditioning. And this can be a major problem, killing all your efforts. If all you think about is just speed or asymptotics or something, then you will run in this problem. Poor conditioning results in a decline of accuracy at higher temporal. You know, the pervert thing is that you will not notice in your small homework example. This is something that you notice if you want to do the real thing. Yeah. So it's always a difference between some poor little metal homework example and building an actual car. And in particular, there is a big difference between building a really good car and a really average airplane. A really average airplane is much more complicated to build than a very good car. Yeah? So, fortunately, there are simple methods, and we should think about the simplest methods first because the simple methods are also the most effective. If it comes to very complicated, I mean, you can use very complicated methods, but squeezing out more performance becomes more and more complicated. Yeah. First things, I mean, this is I write this down here so that you always think first things first. I mean, you could almost just tell me what is the problem and how to solve it. You have an idea.
Simplest measure to condition are also the most effective. What I would guess is that we have to make bigger these. Somehow we have to make or rescale these numbers or make them bigger.
Yeah. Okay. So very, very simple is, of course, you use double precision. So this is always, but this is expensive, of course. Yeah.
Okay.
Yeah. So, I mean, this is. Yeah. Go ahead.
Yeah, I was gonna say that we can maybe sum over the things that have the same scales.
Yes.
So we have more bits.
That's true, and this is one, but this is not the simplest measure. So this is something that we that comes in up in 10 minutes or so. Yeah. So before this, okay. Well, this is a point that we'll take care of. But the first thing is to recognize that this rho 0 is by definition constant. And if you think you need to store a constant, then you are, I don't know. So it is, in a sense, it is useless to store constants. Okay. Yeah, the constant part, because you know what it is. Yeah, so you should. There's no need to store this guy. So and this works like this. So we define a delta fi as an Fijk minus a Wijk, where this Wijk are the constant lattice weights that we also know from the BGK lattice weights. So these are the reasons why this F, so F is a distribution. So distribution, mathematicians will tell you distributions need to be positive. Yeah? So you're only using one part of the floating point spectrum. So they need to be positive. They're not zero, they are larger than 1. So, but from a floating point perspective, you could take their constant part, just subtract it, and then they would be in general around 0, right?
Okay.
Yeah. So and then you have more space. So this the weights are, if you sum over this is the idea. If you sum over the weights, you get this constant part. Yeah. So you'll eliminate it. Now what you actually store is no longer F, but you're storing delta Fijk. And if we stay in this picture with here the most significant bit and here the least, so we are no longer in the fraction, of course. So we are no longer storing row 0. This means what we store in the most significant bit is epsilon u1. Then after this, we store epsilon square theta delta rho, so the pressure, and then we'll go on with the ghosts. Also, and now the observation is that all of them have much more space. I'm always doing this wrong. So these are, again, the effective available bits. And each of them has now more bits. So there is an essential caveat with this. Not because I've explained this a lot of times in my life. I've explained this a lot of times in my life, and I still discovered that this is often done not in the right way. Okay, it is essential that the well-conditioned state that is the one without the delta, without the constant, this is preserved. So what you are not allowed to do under no circumstances, so this need to be preserved, it's unreadable, preserved, throughout all computations. I mean, this has consequences for your equations, yeah? Obviously, that you withdraw, that you subtract this. Now you could have the idea, I get this out of the story, I add this 1 again, do some calculation, and then I subtract the 1. In the moment where you add and subtract, you have killed it. Yeah? So there is this, so you have to keep this. Otherwise, there was no point. Yeah? So remember, the accuracy of the simulation is limited by the, yeah, big the, by the operation with the least accuracy. So then there need to be only one mistake. There is no rule, there is no room for being sloppy somewhere. Yeah, if you want to avoid this, yeah, because this is a chain of calculations, and the chain. So this is the thing that you have to think about. The chain is only as strong as its weakest link. I mean, I'm pretty annoying here. You can run simulations without this, but if you have a requirement for a certain accuracy, then you have to follow this rule. Yeah? So if you need to be in industry precision, this needs to be fulfilled. Yeah? Yes.
I suppose that this here can only be done with incompressible fluids, right?
No, this can be done in both cases. It looks a little bit different in the different cases you do it, but it can be done. It can be done in both cases.
Okay.
So in incompressible fluids, it's common to do it, but it can also be done in incompressible fluids, and then you have to be very, very careful in where you add the one and where you don't add the one in order not to lose data. So now we spent a lot of time talking just about the storage. Now we come to the computation. Data loss in computation. So important thing to remember here. So far, we have not. We only talked about storing data. Yeah, there was no. We did not yet talk about round-off errors in actual computation. Now, usually you would have to combine all the measures together. This can be done, but because we have not so much time, and we'll. And it can be kind of confusing. So what we will do for clarity, we use the unconditioned populations. So we look now at the other problem, and we do as if we don't know about the other, the conditioning. In reality, you have to do both together, okay? So let's look at how you would potentially naively compute your moments. For example, the velocity. So if you go by the book and say this is our velocity u1 or ux, however we call this is 1 over m0, 0, 0, and then we do the sum over I, j, k, and they start from -1 to 1, and we sum over I, f, I, j, k, and this is of course for the D3Q27 lattice, right? So this is the way you can compute the velocity. So what are you doing? You have a summation. You have a summation over 27 numbers, of which 9 are actually 0, but this doesn't matter because adding 0 does not do anything in terms of round off. So I mean, this is concerning round off errors. Adding 0 is for free. Yeah, so it doesn't matter. However, otherwise, there's of course round off errors. Summing n numbers has round off error of the order of n delta. So where by delta we mean the least significant, the value of the least significant bit. Okay, so this is a bit tricky because the least significant bit in the floating point number is of course not constant, yeah? So this depends on how your numbers are, and also has a consequence on how you would do it. And the colleague from the internet here just said it in the right way. We should always add things of the same order, yeah, together. So there is methods that are more accurate to do sums. So for example, there is a thing that's called a Kahn algorithm. That is the one that has the least, that does sums with the least amount of round-off errors that you can produce. So I believe, but this is a very costly algorithm. Yeah. So we want to have everything, and we don't want to pay anything, right? So this is how bad people are, yeah? So, and therefore, we use a more accurate, so there is a more accurate way of doing the sum that has the same cost, but is much, has much fewer round-off errors than just summing up the numbers. So this is the important thing. It is actually the same, has the same number of operations. I mean, in sums, it is difficult to just not do. We'll see that it is possible to actually eliminate operations. I'm running out of time, but we'll anyway talk about this. What did I write? Operations is, so there's a cascade, sometimes it's called the pyramid, or the pairwise summation. And this is actually something that we've already used in the example code. So now something on top that is related to Lattice Boltzmann. Yeah, a pairwise summation is of course something that exists outside the Lattice Boltzmann world too. But here, okay, in pairwise summation, usually the first thing would be that you order your numbers according to your size, which is of course costly because you have to touch all the numbers. In Lattice Boltzmann, so if you want to avoid this, you need to have an idea which numbers could be of what size, and then you could pre-order them. Yeah? Then you are not safe that they are actually in the right order, but it may be better than any random order, right? So, and in what we have to take into account here is that notice that the value of the least significant bit depends on the lattice direction. By the way, this is also the case, even though we argue now with the unmodified populations, this is also the case for the modified populations, just to a different extent.
In our case, the least significant bit is given by the ghost moments, right?
No. The ghost moments does not give the least significant bits. That's, all of them. All of them contribute. Yeah. I mean, the difference is that only the large ones contribute to the first part of it. Yeah. But if you just look at this picture here. Yeah. In the least significant bit, they all arrive. Yeah. It's just the least significant, all of them are present. Okay, so in the D3Q27, which we like to use, we have these weights like this. There's 1 over, so W111 will be 1 over 216. W110 is 1 over 54. W100 is 1 over 27, and then there's W000, which is 8 over 27. So you see they are of different size. So meaning that the least significant bit for the 000 population is larger than the least significant bit for the 100, and then for the 110, and then for the 111. So they have separate classes of direction, or for the directions. And therefore you should order them in a particular way. So let's see how to compute the velocity or the momentum m100, so the first moment. Yeah, so let's see, we'll have different steps, and they say we have step 1. And in the step 1, so we'll divide the different classes. So we have the class W111, which will be F1 JK, so there's different minus F minus 1 J minus J and minus K. Yeah, so we have to go through all the J's and all the K's. Yeah, which means we have different permutations. Say I'll squeeze this in between here. Permutations of these. So we'll have 4 different permutations. So there are 2 indices. Yeah, 2 indices. They give us 4 different permutations. No, it's they go from, so say now that they are this is more than 4. No, yeah. So this is 4 permutations. So then we have the class W11 F10K minus F minus 1 and minus K, and we also have F1J 0 minus F minus 1 minus J 0. So these are the permutations here, and then we have class W100, which is, there's only one of these, is F11 minus F minus 100. F100 minus F minus 100. So, okay, out of these, so this here exists only once. These guys here exist 4 times. These guys here exist 4 times. Yeah. So we do the first step here. Then we add these guys up. So we'll add these. We do a plus of all the permutations. And this is our step number 2. So the first step is the sum, is the difference that we write here. And then the second step is to take 2 of these permutations and add them together, right? So this is the second step. Then you see we have to go on and add these 2 permutations together. This is the third step. And then we go to the fourth step and add these 2 guys together. And then comes the fifth step, where we add this with the last one here together. And what we then have is M100. So what is the difference of, what advantage is that we have with this pyramid? So if we have to add these 18 numbers, 27 minus 9, yeah, 18 numbers, we'll have 17 additions, right? We have 17 additions. So we have 17 times delta, times, suppose that delta would be the same, yeah, 17 times. Now, here we have, instead of 17 steps, we have only 5 steps. We have only 5 steps, so we have only less than a third of the round-off errors. Okay, so number of summons n equals to 18. Naive summation. Okay, I'm a little bit inaccurate now, yeah, saying that, okay, it should actually be 17 delta, because there's the 17 sums that you have. In a pairwise sum, in a pairwise summation, the number of steps that you have is given by the ceiling of the binary logarithm, and don't write binary logarithm of the number n, so, and this is 5. So the error in pairwise summation is of order delta log n, which is usually considerably smaller than the order delta n. And this is the reason why you should always use this cascaded summation. And in Lattice Boltzmann, you should also always try to consider the asymptotic order of the asymptotic size of the thing. So you should order them in the right way. And you may notice what we did is we always combined the antipodes, which is so the one that goes in the one direction and the one that goes in the opposite direction. This leads us now to the last part of this lecture, which is the chimera transform. That is, of course, now the quintessence of most of this. So, I would claim that the Chimera transform is the reason why we can do cumulant lattice Boltzmann in the first place, because this was such a game changer that when we introduced this, this was the first time that we actually saw an improvement over other methods, both it makes it much more faster, and it got much more accurate. I mean, in principle, you can do it without it, but then there are lots of problems with the round-off errors. Okay, now we have to understand what is the problem and what is the solution. So, the cumulant method, this requires a lot of computations, and in particular, it requires a transformation from populations to central moments. And the first naive way is to compute, okay, the reason why this is the case, because we cannot compute cumulants directly, we have to first compute some moments, and from the moments we can then compute the cumulant. So there's a possibility to first compute raw moments, from raw moments central moments, and from central moments cumulant, as we did in the example last time. And if you do this in 3D, you will absolutely kill everything you try to gain. Now you can also compute central moments directly, yeah? And this, again, can be done in a naive way. So the naive way, so we call central moments with K, A, B, C, is the sum over I, J, K equal from -1 to 1 over F, I, J, K, I minus U1 by the power of A, J minus U2 by the power of B, and K minus U3 by the power of C. So I have forgotten whether we call this U, X, Y, Z or 1, 2, 3, but doesn't matter. You know what I mean, yeah? So what you have to do, you have 27 populations all the time, and you want to have 27 moments, yeah? So this is 27 populations that you have to sum 27 times to 27 moments. So you have to sum over these 27 things 27 times. And this happens actually to be the most expensive part of the entire method. So the first thing is the thing that you always notice is that it takes a lot of time. You think about round-off errors always only in the second step, even though it's more important than the other one, actually. Yeah, but say it takes a lot of time. So how to accelerate it? And the solution to accelerate this is actually so simple that everybody who knows this said, okay, this is obvious, but apparently it was not obvious because it took very long to actually come to this idea. And when we had this idea and we wrote it in the paper, actually, the reviewer told us, okay, leave this part out, and this is too trivial. Yeah, but it's not trivial because, good things are always then later said they will be trivial. But the cumulant method exists because there's a chimera transform. Without this, it wouldn't work. Okay, what is the idea? Chimera is something that is part one and part something else. Yeah? So the nomenclature that I use here is maybe a little bit strange, but let's stay with this. Yeah. So we have the indices A, B, C for the moments, and we have the indices I, J, K for the populations. Now say we compute something that is a chimera between populations, and so that is a population in the X and Y direction and the moment in the Z direction. Yeah? And I indicate this. I make here a small line just to indicate that there is a difference. Yeah? So we'll have IJ index, which is population, and C, which is moment. Right? And now we compute this moments. We sum over small k, k from -1 to 1, Fij k, and we do this k minus u3 by the power of c. Okay? So this is something that we have that we have to do for all our 27 populations 3 times. Then when we have this chimera, we use this chimera to compute moments in the y direction from this. So we sum now over j from -1 to 1, and we get here the previous one, kij and c, and we do this over j minus u2 and by the power of b, and again we have to do this 27 times 3, and then we end up with the actual moment when we do the sum where j from -1 to 1 k I b c I minus u1 by the power of a, and again this has the same number of operations. So now this, looking naively on this, is, you would say, is 3 times faster than, you have 3 times less terms to compute. Because previously at 27 times 27, and now you have 3 times 3 times 27, so you have 9 times 27. However, that's not all of it. It's even possible to somehow eliminate common sub-expressions within these things. And you have a question?
No, I was. No.
Yeah, and so and the operations in this are even less. So each term in the chimera transform has fewer operations than in the naive. The savings are even higher. And now, one thing that I have to say here is that there is a big difference between 2D and 3D. So this is in particular important for 3D. Actually, in 2D, it's almost leveled out. Yeah, it will be almost leveled out, even though it's a little bit less than doing the naive way. But in 3D, you see the following. I've used Mathematica to count the number of operations. Oh, sorry, not iterations, operations. And compare the naive way of doing it and the chimera way of doing it. And I count the number of additions and multiplications. So the naive transform has 1,482, sounds a lot, additions. Yeah, one way. Yeah, and it has 1,452 multiplications. Now the chimera transform has 270 additions and 162 multiplications. I mean, I don't need to say that this is a difference. So we have only 1/5 the number of operations. So the next thing is that automatically the chimera transform is a pairwise summation. The reason for this is that the idea of the chimera transform actually is the same as the fast Fourier transform. So the chimera transform behaves to the naive transform, the naive moment transform, as the fast Fourier transform behaves to the naive discrete Fourier transform. And we know also from the fast Fourier transform, yeah, because it does also pairwise summation, that the fast Fourier transform is much more accurate than the discrete Fourier transform. I mean, this is like the, win-win-win, yeah? So you are much faster and you are much more accurate, yeah? Both at the same time. And both for the same reason, because you are saving operations, yeah? So the chimera transform is a pairwise summation. So we made some measurements, and I mean it's really hard to believe, but this explains why it was so difficult before and it's so easy after. So we made, I mean this was just one example, so it's not always the case, but we've seen and measured this, that a single naive transformation could lose in a single application could lose 10 significant bits more. Okay, the chimera transform also loses bits, okay? Yeah? But the naive transform, you do it once. And remember, you have 23 bits, right? And out of this, the naive transform loses 10 more than the chimera transform in one transformation. So, in a particular example, of course, only, yeah? Okay, are still people here? So this was this particular lecture, and I don't want to let you go. I mean, you're all free to go, yeah, but of course, we have planned some exercise for this. Now, since I'm so, you see that I'm very much into the chimera transform. We could now do with our code different things. So, for example, we could work on the conditioning, subtracting 1, and see how this works. But this is not what I prepared for today. Today, we want to look at want to implement the chimera transform here in 2D to see how this is done. Okay, so we'll take our code.
I have a question.
Yes.
Before we start. So the idea here is that we apply a Fourier transform.
So you remember that actually the moment generating function is the Fourier transform of the population. So actually the moment transform is a Fourier transform. Yeah? Yeah, and now you can do this Fourier transform in a different way. So the difference between a fast Fourier transform and the discrete Fourier transform is, okay, there are basically two differences. So the reason why we call it fast Fourier transform is because you're doing the same computation. So computing different Fourier coefficients have common sub-expressions. Yeah. So you do these sub-expressions first. Yeah. So that you compute several of these coefficients at the same time. Because otherwise, how could you do it? If you want to compute just one Fourier mode, then doing fast Fourier is not faster than doing the discrete Fourier mode, because you have to sum over the entire all the numbers. Yeah. So this is one difference between fast and discrete Fourier transform, is that you do these common operations only once. So, but this has a consequence, namely that these common operations, they are all pairwise operations. It's not you integrate from left to right, but you integrate over pairs. Yeah? And this pairwise summation, this is the thing that makes the fast Fourier transform so much more accurate than the discrete Fourier transform. So the idea here is the same, it's exactly the same. Yeah? So we compute not moment by moment, but we compute all moments together in one go. And we do this by splitting it up in different pairs. And this is why it actually, you could say that this is a fake name. You have to give it a name. But actually it is really a fast Fourier transform for computing the moments. Yeah? Okay, so what we are going to do is, the code has become pretty long now. What we are going to do is we're picking up the cumulant kernel that we had. Okay, maybe I'll do this a little bit differently now. Let's see. Okay, not everybody is joining in, but whatever. So we'll take the entire stuff here with all its boundary conditions. Okay, this is not the way you should write code. Yeah. See, we have so many doublings in here. Okay, so copy this and call this here, instead of cumulants, we call this chimera. So I'm chimera. So I should be able to write it at least. So let's do the infrastructure first and say we'll have here another one that we call chimera. So this is the Python bindings, yeah? Otherwise we cannot execute it. Okay, so we need to do a chimera transform, and because this is something that we will use repeatedly, I will put this into the common local functions, which usually are on the top.
Something that can be done to make look everything smaller is if you place the mouse.
Look everything smaller. Why do we want to?
Yeah, because we have a lot of functions. So if we want to go down, if you place the mouse.
You mean we want to close this? Yes. Okay. So we can. Yeah. Okay. So we have a lot of functions. Yeah, you're right. We'll make the function go away. So just the one that we need. Yeah. Thank you very much. Right. So we'll. Python binding, let me see. So no, we are in the wrong place. We will have to be in the non-public sphere, right? Let's close this also. Okay, so we'll write these things in form of inline functions, void, yeah, chimera. So what the chimera transform is is a one-dimensional transform. In 1D, we always have three populations, yeah? And we'll call them, okay, I'll using a little bit my cheat sheet, so we'll call them floats. Oh, by the way, there is, yeah, this is floats. Floats. And I will now pass this by reference. I hope you are familiar with C as much as to know what this means, passing by reference. So I pass KA, KB, and float reference KC by reference, and then we also need the velocity. And then we need the function body. So now, how do we get to, how do we do this? Actually, I've prepared something in Mathematica. We can, because people are running away, we could just use what I've already implemented. Or do we want to write it again? Okay, I think we'll just, this time, I just typed something down. Okay, say I've now done this. So this is we would compute a central moment in one dimension like this. And then we would call this the first. So I've actually executed this already, so we can have, say, the zero moment is just the sum of them, yeah, as we know. Then then we have the first moment looks like this, and we would have to have a second moment. So we have to get out. So they look like this. Okay, I've done this here, and okay, so right. What I wanted to point out is that there are actually some common sub-expressions here. So this term here, you can easily identify as being the zero moment, right? So we wouldn't compute this again. Yeah, we would try to pick this out. And what we have here is actually something that looks very much like the first raw moment, yeah. And if we look at the first moment, yeah. So in the first moment, we also have the first raw moment sitting here, and also there is minus the zero moment. So there is some repetition, yeah. And for this repetition, so the things that we saw repeatedly were the zero moment and the first moment, and then there is something else that we could pick out, namely there is something that you could call the second moment. So we have here F1 plus F minus 1. It's not well ordered here, but this is something that also appears in here. Yeah? So then, and this actually is the second raw moment. Yeah?
Okay.
Yeah? So
Yes.
then we have a reason to first compute. Okay, so now we can do this in a clever order. Yeah? Because the zero moment or the second moment, the second raw moment is inside the zero moment. Yeah? So what we would do then is to compute the second raw moment, M2, first. Yeah? And we mean Ka is now, okay, I have used a little bit strange nomenclature. So why do I call these things? So we are talking about chimera, yeah? Now there's one interesting thing is, since we are always getting the same information, the same amount of information out that we put in, we can actually override the input, yeah? Which we call in-place transformation.
All right.
Yes? So what comes in here will first be, so enters the populations, exits the moments. Yeah? So, and with Ka, I'm referring to -1, with Kb, I'm referring to 0, and with Kc, I'm referring to, okay, maybe Ka is -1, Kb, okay, let's put a column or something. Let's -1 Kb is 0 and Kc is 1, right? So, okay, Ka plus Kc. Yeah, so this is the second moment. And then we also have the first moment, M1 is Kc minus Ka. This is the first moment. So then we can, though what we want to have is that in place transformation to moments, meaning here that A or Ka is becoming K0. Okay, maybe we'll do it like this, yeah? It should actually be an index, but so then this Ka is K0, Kb should be K1, and Kc should be K2, okay? So means that we want now that Ka is the zero moment, and the zero moment is this M2 plus Kb, right? So because we are doing operations in place, we have to make sure that we do these operations in the right order, yeah? Because now we know, previously Ka has been the incoming population, and now it's the moment, right? Little bit strange, yeah? But this saves us a lot of in-between operations. Okay? So this is K. Now KB is supposed to be K1, and K1 is this M1 minus U times now Ka, because Ka is now the first moment, the zero moment, right? So, and then Kc is supposed to be the second moment, and the second moment is M2 plus U times minus 2 times M1 plus U times Ka. Okay, so now I was just typing this from my notes, but this is what you get, what you actually see in here in this mathematical result. So this is the K2, right? So this has M2 is this one plus this one. Then there is 2 times M1, yeah, and then there is U. Then there is U times K1, and I put the U outside and put this in the sum. So it's the same thing, okay? So now we have done this transformation. Okay, we've implemented this transformation, and what the transformation is supposed to do is to replace this all of these transformations. So we'll want to go directly to the central moments. So now it becomes very tricky, because I just noticed I don't have a sheet. I don't have this on my cheat sheet. So we need to be able to implement this ad hoc. Yeah. So now we can.
They have to be in order, or do they have to follow some order with the moments also, or it's just in the transformation?
They need to be given in the correct order, in the order that we specify. I mean, so here we compute the moments. This is something that we don't want to do anymore, right? We are in cumulant, right? Yes. So we'll want to get rid of all of this. Okay, do we want to get rid of until here where we compute cumulants, yeah? Okay, let's keep it this way. So actually what we leave is computing the populations like this, yeah? So now what we have is we want to get to this central moments here, yeah? But first we load them with the populations.
Didn't you create a function called run chimera? Because if we work right now in cumulant, the bind, we would need to call cumulant to run chimera, right?
You are so right. We wanted to do this in run chimera. Thank you very much. Okay, so getting started again, yeah? So these guys, so all of these guys, we want to get rid of them. Boom. Okay, I keep them for the time being. So now we want to do this in-place transformation. This means we have to initialize our quote-unquote moments with the populations. in the right order. So we need to have, for example, K00, and this is now to be now this may be a little bit confusing, because you know the trouble always is that moments go from 0 to 2 and populations go from -1 to 1. Yeah, so the K00 would be the one -1 -1, right? So that's a pity. But how should we do it otherwise? So let's see, how is this called? This is f. This would be f -1 -1 of x and y, right? And y. So then float K01. So K01 is Fm, and now 0, Martin Schöner always says 1 is 0. Yeah? Yeah? Unfortunately, because we go one step on. X and y. Okay? So now what we are going to do, we have to do this 9 times.
K02 would be F.
What did I do?
K02 would be F and P.
K02. Do we want to continue with K02? Okay.
Or do we need, no, we don't need K0 to be, because we are working just with one, or no, do we need?
Okay, you know what I'm going to do is when I do things like this, I like to change indices in the Cray code fashion.
Okay.
Yeah, so that I only change one index.
Okay.
Yeah, every time, so that I can compare to the previous. I change only one index. This is not mandatory. This is just my style of doing stuff. Yeah. I don't know. This is not the correct Cray code, I believe, but so it helps me making less mistakes. So if we go to 2, this will be P, right?
Yes. Okay.
So, and then I didn't take particular care about real Cray code, so the thing is just we want to change this to, for example, now we have this at, we did this in a stupid way. Okay, okay, I am just changing, this is not real Cray code, it's just changing one at a time, yeah? So, okay, we'll have to pick them all up, meaning that we now have to go to 1 here, and if we go to 1 here, this will be a 0, and then we go to 0 here, and then there will be a minus here in M, to 0 here, and then we go to 1 here. So how many? 1, 2, 3, 4, 5, 6, 7, 8. What is the last one? Which one have I? 0, 2. Okay, this means, this is I put them in the wrong order. I put them in the wrong order because so I can no longer 0. Okay, I'm actually missing 0, 2. How could I repair this? I cannot okay, let's see. Okay, we are not perfect. It's not Cray code. right? Just do it, yeah? So 0, 2 means that this is minus and plus, right?
You could, if you wanted to.
By the way, I made a mistake here, right? So this is 0.
Yes.
Yeah, I can reorder them that they are correct, I know. So is one.
Maybe 0, 0, 0, 1, 0, 2, and then 1, 2.
Are you insisting? And we will.
No, I'm just. I was just.
Okay, this can be done in a better way. This can be done in a better way. Yeah. Okay, we always say it's Friday. It's 1:45. We want to. Okay, so all we did is storing the populations in these local variables. By the way, which you should do anyway, even before you compute the velocity, but we are not trying to be perfect today. We are just looking at the principle how to do it. So now we have to do the Chimera transform, and we have to do this for each part of these directions at once. So we do it first in the x direction, I suggest. So we'll vary the x direction. So we have k 0, 0, k 1, 0, and k 2, 0, right? And then we'll have ux at our local position. So this does the Chimera transform here for all the values with the y direction being 0. Yeah? So we'll have to repeat this for all the other directions. So in 2 dimensions there's only 3. So we have to repeat this here, here, and here. So this is the other combination, and then we have a third combination. So, and then we have transformed, then we did the transformation in the x direction, and there are still populations in the y direction. So we turn everything around and do everything again in the y direction. So let's do it again. Do everything in the y direction, so 1 and 2, and here we have to use the velocity in y direction, and do this 3 times again. So we have to do this for these guys, and we have to do it for these guys. So, and now what we have done now is we have implemented the forward transform. Yeah? There will also be a backward transform, but we've already implemented the backward transform. It is so the backward transform is this here plus this here. Yeah? So this is the old-fashioned. So now what we are going to do is we try to compile this stuff. Am I using the right one? We are trying to compile this stuff and see whether it runs with the forward transform Chimera and the backward transform naive. Okay? Yeah? Because we always do things step by step.
But then there's also a fast. Well, it would be from.
Yeah.
So there's also a fast Fourier. Yes, of course.
Backward. There's also inverse fast Fourier transform. Okay? So we have to restart this, and I guess I played around with this. So 100 by 100, 1.996, and nothing fancy here. So this is the usual cumulant way. Yeah. So let's run our cumulant. The old kernel, yeah, for a few seconds. Okay, so this is the usual cumulant kernel. We are not expecting much I mean, we are not expecting much difference. It should work the same way, yeah? So let's stop this and replace this by Chimera. And see whether it runs. I have no idea what we did. And we get, wait, was there a problem?
I think that was the kernel restarted?
Oh, I think we restarted the kernel. At least I pressed this button. Let me see again. No, what is the error? Object has no run Chimera. So, okay, we have to figure out why we have no run Chimera. So we have here run Chimera. We have run Chimera. Wait, this was only, what did I do? Did I compile the right one? LBM demo.
Maybe saving before.
I did not save it. Oh my god. No, wait, so. Okay, I did not save it. Hopefully this was the mistake. Error. Expected, what is it? Is not a member of run Chimera. Okay, well, what is the error? Function definition is not allowed. Okay, I made some problems with the brackets, I guess. There needs to be something wrong with the brackets. But it looks, no, this looks right. What is the line 571? 500. Wait, was it that I killed? What is the?
It's this function run Chimera is
okay, I mean,
inside cumulant.
So okay, let me see whether this. So we lost a bracket when we copied. Okay, I see the problem. Okay, what we've gotten to do is that we did not, in the back transform, we did not initialize these things. So okay, you see, it never runs out of the box. Wait, was the error Chimera was not declared in the scope?
The inline function has another name. Then
Has it a different name? Run.
the first one, the one that was, yeah, that one.
Okay, I did not write it correctly. Sorry for that. So this was only the warnings. Okay, so now we got only warnings. If not repaired the warnings, restart. Run. Wait, this was only warnings. Has no attribute run Chimera.
I suppose that there is still something why it does not run. There might be still something with the brackets.
Okay, I'll. But it apparently compiled. So all on the recording, you know, we always make fun of ourselves by not seeing the obvious. So there were warnings, but and in this blah 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 blah. So we put LBM run Chimera. So that for me looks like there is, unless I misspelled it again, run Chimera. Did I misspell it? Restart, and run. Has no attribute run Chimera. That now becomes unexplainable to me.
Could you please try to close the function, both functions, cumulant and chimera?
Which one is this one, the cumulant one?
Okay. Yes, we are separate.
Chimera, so now they look separate. Now this looks like it has compiled it. It gives warnings, but it's compiled.
Oh, there's one.
Okay, wait, this was not declared. Why is this? Oh. How can... I was hoping that it gives the errors last.
Maybe the warnings, yeah, because I give them in order, so that means that the warnings
The warnings override the errors.
the first errors and warnings, and it's in order.
So now I don't see an error now. Okay, sorry for this. Thank you for still being here. But you see, this is real. This is the life. This is real world. Okay. So you see, it works. Yeah, you just have to be persistent. Yeah, we've implemented this transformation correctly. So let's stop this and think about something else. Now we want to have the opposite way also. Unfortunately, with the opposite way, it is not as easy to find common sub-expressions. So now let's be lazy and say I've already implemented this, yeah, like this. So what I do is I make a table of KKA is this KA. This is the one that gives me automatically the expressions in terms of populations, right? So then the KK is the one that I keep as a variable. And I do this for A from 0 to 2, and then I solve this entire stuff for the different populations. Meaning, I get the populations in terms of the moments. Yeah, and I also try to collect them and try to simplify them, but as you see, there is not much simplification going on. So I will now take because this is usually something that I have to rearrange a little bit by hand, and so I'm not going to copy this, but I'm just writing this by hand, and I'm using my cheat sheet because unlike on my big computer, it's not easy to put these two windows next to each other. Yeah. So what we do is we write an inline function, inline void inf chimera, and in this we do now the same thing. We give a float passed by reference so that we can a modifiable variable. Yeah, I think in Python they call it modify pass and also something like this. Yeah, a modified variable, modifiable variable, float, modifiable, passed by reference, KB. Float, I should actually just copy this from above, but anyway, float, modifiable KC, and non-modifiable velocity, float U. Okay, so this was the mistake that I just did. Yeah, I did not write float in front. Okay, so now we have to take care that we do not overwrite stuff, and therefore I have to have two variables here, namely km, so this is the minus part, km, and according to the equation that we had here, I've tried to rearrange this a little bit by hand. This will be Ka times U times U minus 1.0. Yeah, by the way, if you look at it, okay, we are talking about the minus part, yeah, first. And you can see these are similar to the one part, just by this minus it is different, and by this minus it is different, which is a bit unfortunate because then you cannot take these things out and pre-compute them because they will always be different. They're also different from this here, right? So, okay, we'll write this here first, and then we just change the signs of this. And of course, we put the 1/2, you know, this is everything multiplied with 1/2. We'll keep this outside. Yeah? So, okay, we are here in K. U times, what did I do?
In line 79.
Okay, I'm in the wrong line, right, yes. U1 is U times U1, right, okay. Plus KB times 2.0 times U minus 1.0, the thing plus KC. So this is the thing, I'm kind of having the wrong 0.5. So this is divided by 2. Yeah? So, and now we see that the same thing, just with different signs. This is why I'm going to copy this. The same thing, just with different signs. Turn up here. So this is here plus, and they will be plus here. So these are the two different signs. And then the last thing, so now we have, oh, wait, sorry. This is KP, of course, yeah? So now we do not, because we are doing in place, we do not need to save anything anymore. We'll just store KB. KB, because we have not overwritten any of these, yeah, so far. Yeah, we can write KA times 1.0 minus U times U. What did I do? KB is equal to KA 1, so minus 2.0 times U times KB minus KC. So this is supposed to be, the part that is here coming from 0. Yeah? And then we just store the other things, Ka, because we're passed by reference. We store Km into Ka, and we store Kc into Kp into Kc. That way around. Okay, now we have implemented the inverse Chimera transform. So now we go back to our, we've closed it. I have to open it again and see what we do in order back to raw moments. Okay, now we'll have okay, now we do this here as our transform. We do this as our transform, and this is something that we are going to do no longer, right? Instead, we're doing the inverse Chimera transform. Okay, inf Chimera. Now the same as above, right? K00, K10, K20, and the thing is U, X, and Y. Just everything the other way around. Then, the same with this being 1, 1, 1, and the same with this being 2, 2, 2, 2, 2. Now we did it in one direction, now we have to do it in the other direction. The other being Y. So the other being Y. And go through, oh, wait, no, that was not good, sorry. Don't do it this way. I feel very sorry for the people who try to follow this in the internet, because I'm so lazy that I don't cut out the problems that we have in between. You have to go through all of this yourself. Okay, so now we have done this transformation. Now, after the transformation, I mean, So this was just, so previously, this here, that does not look so bad, yeah? It's just a transformation from the central moments to the Ra moments. But then we have to go from the Ra moments to the populations. And this, so this is another transform that now we do not need any longer. Yeah? So instead of this, we just have to identify our population. So I'm being lazy and just, oops, what happens? And keep this in. And now we have to set here our right moment. And now, as Martin said, 0 is, okay, 0 is in this format is K11. Okay, because I'm now, it's 12 o'clock, I didn't have my lunch. See, 0 is 1, 1, right? Yeah? F0 is 1, 1, okay? So let's try to survive with this. So K minus 1 is here 0, and 0 is 1. Okay, I don't like to say this. Kp is becoming 2 and 0 is 1. So K 1 0, right? Yes. This is why the code looks crazy later. K1, okay, 2, yes, K1, 2, right? So minus is K0, 0. K2, 2. K2, 2. K2, 0, K2, 0, and K0, 2, right?
Yes.
Okay. Do we believe this?
Yes.
That's called why it's called Z, because I didn't save it. I did not save it. I mean, that would be a good thing, because then it would look like it worked. Okay, I did not save it in time. So we'll have to compile it again, sorry. I didn't understand this warning. Okay, let's just believe it. Yeah, I don't know. Let's just believe. So if it does not work, it proved that we saved it, right? So we actually should hope that it doesn't work. But if it works, we just assume we are done. Okay, let's run it. It's believable that it runs. Okay? I don't know whether we see any difference in principle that could now be a little bit more accurate because of fewer round-off errors, but this is something that we probably don't see in this particular case. Yeah? But we were now able to replace the strange transformations from populations to Ra moments to central moments by hand with the Chimera transform, which in 2D already gives us some more compactness, but in 3D is really essential actually to run everything. Okay, yes, then thank you for attending. I will stop all the recordings.
I have some practical questions.
Should they be on the recording or should we?
No, I think you stopped the recording.
Yeah.